Hello everyone, welcome to lecture 2 in the Ionic Equilibria and Aqueous systems. So let's continue our lecture with acid-base titrations. So in an acid-base titration, the concentration of an acid is generally determined by neutralizing the acid with a solution of a base of known concentration. Remember that here we have an unknown concentration of an acid and we are using a known concentration of a base to determine the actual concentration of the acid. So to achieve that, we achieve what we call the equivalence point. So the equivalence point of a reaction occurs when the number of molecules of OH minus equals the number of molecules of H3O, number of moles of H3O plus originally present, or vice versa. Now the end point generally occurs when the indicator changes color. So this is the reason why the indicator should be selected so that its color change occurs at pH close to that of the equivalence point. So this is a curve that shows the strong acid, strong base titration. So let's say we have titration of a 40 ml 0.10 m HCl with 0.1000 m NaOH. Now what will happen initially is that the pH of HCl is very low, so which means it starts at a really low value. Now as you give more and more NaOH, you start noticing that the pH value starts increasing, and at a certain point it increases rapidly and it achieves the equivalence point. And once it achieves the equivalence point, the pH tends to go really rapidly and starts increasing gradually when more base is added. Now remember that the pH rises very rapidly at the equivalence point, which occurs at a pH of 7 for strong acid, strong base titrations. So how do you calculate the pH using a strong acid, strong base titration? So the initial pH can be calculated by the initial concentration of the acid. And the pH before the equivalence point, first we try to calculate the initial amount of H3O plus, which is the volume of the acid times the molarity of the acid, and the amount of OH minus that's being added, which is the volume of the base times the molarity of the base. And finally, the amount of H3O plus remaining equals the amount of H3O plus initial minus the amount of OH minus that you have added. So how do you calculate H3O plus? It is the remaining amount of H3O plus over the volume of the acid plus the volume of the base. So from that, finally we can find the pH of the final solution. So pH generally is about 7 for a strong acid, strong base titration at the equivalence point. Now beyond the equivalence point, once you cross it, how do you calculate the pH? We already have the initial amount of H3O plus and we are trying to calculate the added amount of OH minus. Remember that when we exceed the equivalence point, we are adding more excess NaOH, which is going to be found out by using added OH minus the initial H3O plus concentration. So we calculate the POH by calculating OH minus, which is the number of moles of excess OH minus, and over the volume of the acid plus the volume of the base, which gives you POH. And finally we can find pH using the formula 14 minus POH. So let's take an example problem. So what is given here? You have 40 ml of 0.1000 m HCl is titrated with 0.1000 m NaOH. So first we need to calculate the initial concentration of H3O plus, which is going to be the initial concentration of the acid, which is 0.1000, so 0.1000 m. And the second thing we have to calculate, so first thing, let's calculate the initial pH. So the initial pH is going to be negative log of H3O plus, so which is going to be negative log of 0.1, so which gives you a value of 1. So the initial pH is 1. Now we are trying to calculate the amount of NaOH being added. So we are titrating it with 0.1000 m NaOH. So let's say we are adding 20 ml of NaOH. So let's start with 20 ml of NaOH, which is the volume of the NaOH that's being added. Now, once we have added that, we already have to find the initial number of moles of H3O plus, which can be calculated by the volume of the acid times the molarity of the acid. So we have 40 ml of the acid times the molarity is 0.1, so it gives you a value of 4. So 40 ml can be written as 0.04, so this becomes 4 times 10 to the power negative 3 m, mole. Now this is the initial amount of H3O plus. Now number of moles of OH minus being added becomes again the volume of the base times the molarity of the base. So the molarity of the base again is 0.1. That's what we're using right here. So we have the volume of the base, which is 20 ml, which can be written as 0.02 times 0.1. Again, that becomes 2 times 10 to the power 83 mole. Now, the amount of moles of H3O plus present becomes the moles of H3O plus initial minus the moles of OH minus added. So which becomes 4 times 10 to the power negative 3 minus 2 times 10 to the power negative 3. So H3O plus so the moles of H3O plus present. So the excess amount of H3O plus that is left here becomes 2 times 10 to the power negative 3 m. So from this we can calculate the pH. So before calculating the pH, let's calculate the concentration of H3O plus that is present. So that is going to be the number of moles of H3O plus excess over the volume of the acid plus the volume of the base. So which is going to be 2 times 10 to the power negative 3 over 40 ml by 60 ml, 20 ml. So that gives you a value of 0.06. So when calculated, that value gives you 0.0333 m. So from this, if you calculate the pH, it becomes negative log of 0.333. So that pH value becomes about 1.48. Now after you add 20 ml of NaOH, this is the amount of pH that's present. So you can also try the same problem with 40 ml and 50 ml and see how the value of the pH fares. Remember that the value of pH when you do 40 ml, the final pH that you just calculated should equal 7, and this value when it is 50 ml, so this is greater than 7, so which means you will have to calculate the amount of OH minus excess. So the excess amount of OH minus present, first calculate POH. So using these formulas right here, so beyond the equivalence point, using these formulas, calculate the pH finally. So this is how you can calculate the strong acid, strong base titration of an acid. So next, let's look at the curve for a weak acid and a strong base titration. Now, notice that here, the curve rises gradually in the buffer region because the weak acid and its conjugate base are generally both present in the solution during this buffer region. That's the reason why they resist change to the pH as much as possible. That's the reason why the curve is much more bent rather than directly going upward. It's much more slower or gradual. So the pH at equivalence point would be a little higher because of the fact that we have a weak acid and a strong base. So the equivalence point is one that's going to go towards the side that is stronger. So which is the side stronger here is the base. So the pH point will be, the equivalence point will be greater than 7 due to the the reaction of the conjugate base with H2O. And remember that the initial pH is higher than for the strong acid solution, and the pH increases gradually beyond the equivalence point. So how do you calculate the same here? First we calculate Ka, the initial value. From that you can calculate H3O plus, the initial concentration of H3O plus, which is the acid ionization constant times Ha under square root. And from that you can calculate the pH. Once before the equivalent point, using the Ka formula, we can calculate H3O plus concentration, which is Ka times Ha by A minus, or we can directly calculate the pH using the Henderson-Hasselbalch equation, which is pKa plus log of base by acid. Now pH at the equivalence point becomes A minus times H plus H2O gives you Ha plus OH minus. Notice that the pH is on the OH side, so to calculate OH minus we write square root of Kb times A minus, where the A minus becomes the initial concentration of the acid over the acid volume plus the base volume, and Kb can be calculated as Kw by Ka. And finally, we can calculate the H3O plus and calculate the pH. Now pH beyond the equivalence point, we have to calculate the OH minus, where you have excess OH minus, and then finally calculate the H3O plus, giving you the pH value. So let's start with the problem right here. So they're asking us to calculate the pH during the titration of 40 ml of 0.1000 m propanoic acid, where HPR, which is HPR, where Ka value is 1.3 times 10 to the power negative 5, after adding the following volumes of 0.1000 m NaOH. So what is given here? So first it's 0 ml, second it's 30 ml, 40 ml and 50 ml. So first in A we have 0 ml. So we have to calculate the amount of H3O plus present, which can be directly written as Ka times the initial concentration of the acid, which is going to be square root of the Ka value is 1.3 times 10 to the power negative 5 times the initial concentration, which is going to be 0.100 m. So which when calculated gives you a value of 1.1 times 10 to the power negative 3 m. And from this you can calculate the pH. So where you get negative log of 1.1 times 10 to the power negative 3, so which gives you a value of 2.96. So which is the pH of the initial solution that we have started. Notice that here we haven't added any of the base yet. Now in the B problem, it's given that we are adding about 30 ml of it. So 30 ml of 0.1000 m NaOH. Now we have the initial pH value. So the next thing we have to calculate is the initial amount of acid, that the initial number of moles of acid that's present. Initial moles of H3O plus. So initial amount of HPR. So the amount of acid that is originally present. So we have to calculate the initial amount, which is the number of moles. So which means we have to calculate the molarity of the acid times the volume of the acid. So the molarity of the acid is given as 0.1 times the volume of the acid initially present is 40 ml. So which is going to be 0.04. So it gives you a value of 4.10 to the negative 3 moles. So this is the initial amount of HPR. So next we have to calculate the amount of NaOH being added. Again, the molarity of the base times the volume of the base. So which is 0.1 times 0.03, which gives you a value of 3 times 10 to the negative 3 mole. So we have calculated the number of moles of each. Now let's draw the reaction table. Remember here it's a weak acid, so which means that it's not the total amount of acid that's going to undergo the titration reaction. So first we have initial, change and equilibrium. So you have HPR reacting with OH virus gives PR minus plus H2O. Now the initial value, the initial amount of HPR that is present here is 4 times 10 to the power negative 3, which can be written as 0.0004, and the amount of OH minus is 0 and PR minus is also going to be 0. Now we are adding an OH minus value, so we are adding an OH minus of 0.003. So which means this is entire amount is being utilized by HPR. So we can write negative 0.003, negative 0.003, and this becomes positive 0.003. Because the equal amount of OH minus that's being used creates the amount of PR minus. So this becomes 0.001, and this becomes 0.003, and this becomes 0. Now we have to calculate the amount of H3O plus that is present here. So that value becomes Ka times HPR over PR minus, or we can directly use the formula for pH, which is pKa plus log of base concentration by the acid concentration. So the base concentration is Pr minus over the acid concentration, which is HPr. So which is going to be negative log of 1.3 times 10 to the power negative 5 plus log of Pr minus is going to be 0.003 over 0.001. So when calculated finally, that pH value should give you a value of 5.37. So notice that initially the pH was 2.96. When you add 30 ml of it, you are achieving a pH value of 5.37. Next, the same thing with 40 ml. So do it the same value at 40 ml. So once you do 40 ml of NaOH, so this is the equivalence point here, where the amount of OH minus being added equals the initial amount of the acid. So therefore, the amount of Pr minus that is present becomes the total amount of number of moles of the acid over the total amount of acid plus base. So which gives you a value of 0.05. So because Pr minus is a weak acid, we can calculate Kb, which is going to be Kw by Ka. So which gives you a final value of 7.7 times 10 to the power negative 10. So from the formula H3O plus equals Kw by under root Kb times Pr minus, you can get the value of H3O plus, finally calculate the pH value. So this pH value is the equivalence point. So this is the equivalence point. Again, when you have 50 ml, you will have excess OH minus. From the excess OH minus, you can calculate the H3O plus concentration and finally figure out the total amount of pH. Next, let's talk about a weak base and a strong acid titration. So again, here also you will start with a high value of the base, but you start noticing you have a buffer region because you have a weak base and its conjugate acid that buffer the effect of the strong acid. And once it reaches a certain point, once it crosses that point, it achieves the equivalence point. Now this equivalence point is less than 7 because of the reaction of the conjugate acid with H2O, thereby resulting in a pH value of less than 7 for the equivalence point. Finally, we have the curve for the titration of a weak polyprotic acid. So for polyprotic acids, you will notice that you have multiple buffers, so multiple buffer regions. The main reason is because of the fact that you have polyprotic acids that have multiple protons that can be donated. So which means that they can have two different equivalence points because the base, the conjugate base of the acid can also act as a base in the second instant, resulting in two weak acid strong base curves. So this is the idea behind a weak polyprotic acids reactions. Next, let's talk about amino acids as polyprotic acids. So the general formula of an amino acid, you have an amine group attached to a carbon which also has a COOH group attached with an R chain. The R here is the side chain that we consider it. Now an amino acid contains a weak base which is NH2 and also a weak acid which is COOH in the same molecule. Because they have both of them at the same time, they can protonate, resulting in the formation of a Zwitter ion which has a neutral pH, and they can also unprotonate it, resulting in a high pH value. Because both groups are protonated at low pH and the amino acids behaves like a polyprotic acid. So several amino acids have charged R groups to NH2 and COOH. So these are some of the essential structures, normal structure of many proteins. So one of these diseases that has this abnormality is sickle cell anemia. So where the hemoglobin has two amino acids with neutral R groups instead of charged groups. This results in an abnormal shaped hemoglobin, causing the red blood cells to have a sickle shape, which results in not enough oxygen being carried by the cell, resulting in cell death or hypoxia, where you do not have enough amount of blood being supplied to the organs. Next, let's talk about equilibria of slightly soluble ionic compounds. Now, any insoluble ionic compound is actually slightly soluble in aqueous solutions. So we assume that very small amount of such a compound that dissolves will dissociate completely. Now, for a slightly soluble ionic compound, equilibrium exists between solid solute and aqueous ions. For example, let's take lead fluoride, where you have the dissociation into lead ion and fluoride ion. But this value is so small that the reaction coefficient can be written as Pb2 plus times F minus square by Pb of 2. So we use another product called the solubility product, which is going to be equals to, so which is the product of the ions, so the concentration of the ions in the QC value, so which can be written as QC times PbF2, which gives you Pb plus times F minus square. So what is this QSP? So QSP is the ion product expression for a slightly soluble compound. So for any compound MQ times XQ, so MP times XQ, which consists of Mn minus, Mn plus and Xz minus. So the XSP can be written as Mn plus to the power P and Xz minus to the power Q. So when the solution is saturated, the system is at equilibrium and this QSP value equals the KSP value. The KSP value here is called as the solubility product constant, and this value of a salt indicates how far the dissolution proceeds at equilibrium, which is basically the amount of saturation. Let's talk about metal sulfides. So metal sulfides behave differently from most other slightly soluble ionic compounds because the S2 minus ion is really strongly basic. So the dissociation results in the formation not just of the S2 minus. Let's take the example of MnS. So MnS doesn't dissolve directly to form Mn plus S2 minus because the S2 minus is really strongly basic. It reacts with water to create HS minus plus OH minus. Now when you calculate the total reaction, you notice that S2 minus is gone. You get MnS plus H2O. It gives you Mn2 plus HS minus plus OH minus. Now this when calculated in terms of the KSP formula. The KSP formula is the concentration of all of the products, so which is going to be Mn2 plus times HS minus times OH minus. For any other reaction, for example, if you have PbF2 which resolves into form Pb2 plus 2F minus, we can write KSP directly here as the concentration of Pb2 plus times the concentration of F minus with the coefficient written on the power directly. But only for sulfides, when you have a sulfide, we will have to write it as HS minus times OH minus. So what are they asking here? Write the ion product expression at equilibrium for each of these compounds. So first they're asking you for magnesium carbonate. So magnesium carbonate is MgCO3. So when split, it becomes Mg2 plus CO3 2 minus. So now, how would you write the ion product expression? So it can be written as Mg2 plus times CO3 2 minus. That's it. Next, the second one is iron 2 hydroxide. Iron 2 hydroxide is FeOH taken twice, so which resolves to form Fe2 plus 2OH minus. So again, the coefficient goes to the power, so KSP can be written as concentration of Fe2 plus times the concentration of OH minus square. So use the same principle, try to doing it for calcium phosphate, which is Ca3PO4 taken twice, and silver sulfide. So silver sulfide, which is going to be Ag2S. So these are the solubility product constants for selected ionic compounds at 25 degrees centigrade. So where you start noticing that aluminum hydroxide, which has a really small value, to zinc iodate, which has a really high value. So depending on the salt, the KSP can be found separately. Now, so let's try and solve a problem. Lead 2 sulfate is a key component in lead acid batteries. Its solubility in water at 25 degrees centigrade is 4.25 times 10 to the power negative 3 gram per 100 ml. What is the KSP of PbSO4? So first we'll have to find out the amount of PbSO4 that is present here. So how would you write PbSO4's reaction? It can be written as Pb2 plus SO4 2 minus. Now the KSP formula can be written as the concentration of Pb2 plus times the concentration of SO4 2 minus. Now the question here is, notice that the value that is given here is written in gram per 100 ml. So write down the actual values. First we'll have to calculate the actual concentration of the H3O plus, the amount of PbSO4. So the mass that is given right here is 4.25 times 10 to the power negative 3 grams, and the volume that is given is 100 ml. So 100 ml can be written as 0.1 liter, and we have to calculate the number of moles. So the number of moles is mass by molar mass. So we have already given us the mass of the PbSO4. So we have 4.25 times 10 to the power negative 3 times PbSO4's molar mass can be written as 3.303.3 gram per mole. So where the number of moles, which can be calculated becomes 1.4 times 10 to the power negative 5 mole. So this is the number of moles. So we need to find the molarity here. Molarity is the number of moles by volume. So the number of moles is 1.4 times 10 to the power negative 5 by 0.1 liter. So which when calculated finally gives you a value of 1.4 times 10 to the power negative 4 m. So this is the concentration of PbSO4 that is totally present inside the solution. Now we will have to calculate. Notice that 1 mole of PbSO4 results in 1 mole of Pb2 plus and 1 mole of SO4 2 minus. So how do you calculate the Ksp value? So the Ksp value becomes the concentration of Pb2 plus times the concentration of SO4 2 minus. So which is 1.4 times 10 to the power negative 4 again times 1.4 times 10 to the power negative 4. So which finally gives you a value of 1.96 times 10 to the power negative 8, which is the value of the Ksp, the ion solubility product. So use the same principle here for problem B as well. So in problem B, you have lead 2 fluoride is shaken with pure water at 25 degrees centigrade. The solubility is found to be 0.65 grams per liter. So you have the mass, which is 0.64 grams, and volume, which is 1 liter. So first convert the mass into the number of moles, and then number of moles into molarity. So the number of moles can be calculated as the mass by molar mass, and finally find molarity, which is number of moles by volume. We know that 1 mole of PbF2 here. So this is a little trickier because notice that it becomes Pb2 plus 2F minus. So which means 1 mole of PbF2 results in 1 mole of Pb plus and 2 moles of F minus. So calculate the F minus concentration based on this ratio, and finally use the formula for Ksp. So the Ksp formula becomes Pb2 plus times F minus square. So calculate from this the Ksp value. So that's how you get the final answer. Next, what is given here? You have calcium hydroxide is a major component of mortar, plaster, and cement. Solutions of CaOH2 are used in the industry as a strong, inexpensive base. Calculate the molar solubility of CaOH2 in water if the Ksp is 6.5 times 10 to the power negative 6. So remember that we generally write dissolution equation, which is CaOH taken twice gives you Ca2 plus 2OH minus. So they have given us the Ksp value, which is Ca2 plus times OH minus, which is going to be 6.5 times 10 to the power negative 6. Now the idea here is to remember you have CaOH taken twice, resulting in the formation of Ca2 plus 2OH minus. So let's write the reaction table: initial, change, and equilibrium. So we don't need to know what CaOH taken twice becomes. So initially there's 0 amount of both. Now if this increases by plus S, this increases by plus 2S. So which means this becomes S and this becomes plus 2S. So this is the solubility of these compounds. So from this the Ksp equation becomes Ca2 plus times OH minus square. So which can be written as S times 2S square, which can be written becomes 4S cube. So the Ksp value given here is 6.5 times 10 to the power negative 6. So 4S cube becomes 6.5 times 10 to the power negative 6. So S cube becomes 6.5 times 10 to the power negative 6 by 4. So that value you have 6.5 times 10 to the power negative 6 divided by 4. So which when calculated gives you a value of S cube equals 1.625 times 10 to the power negative 6. Now if you take the cube root of the answer, so cube root of the answer, that value gives you so S value, which is going to be 0.227. So this is the S value. I'm sorry, this value is 0.0117, which can be written as 0.012, so which is the solubility value of the actual salt that is given, which is CaOH taken twice. So that solubility is 0.012 m. So let's take a look at the cation anion ratio and the solubility. So what is the relationship between Ksp and solubility? So the lower the Ksp value, the higher the solubility. So this is the idea, and the higher the Ksp value, the greater the solubility, as long as we compare the compounds that have the same total number of ions in their formulas. Now if you have the same total number of ions in your formulas, so the higher the value, the higher the solubility. But if you have the ratio that is much more skewed, then there is going to be effect of it on the solubility. So this is the effect of common ion on solubility. So here remember that because there is less solubility towards the right side, the equilibrium always goes towards the left, which results in the formation of the salt itself, resulting in the non-formation of the final compound, so resulting in the precipitation of the salt. So remember this to be the common problem here. So in the last problem we calculated the solubility of CaOH2 in water. So what is the solubility of 0.10 m CaNO3 taken twice? So the Ksp of CaOH taken twice is 6.5 times 10 to the power negative 6. I think the problem is it's still CaOH taken twice. So they're asking us to calculate the solubility of solubility in 0.10 m CaOH taken twice. So again, we know that CaOH taken twice under separation becomes Ca2 plus 2OH minus. So we have the Ksp value which is given, which is 6.5 times 10 to the power negative 6, and when calculated, so we have already started with a solution which has 0.10 m CaOH2. So the solubility of the actual CaNO3 is already given here. So the solubility of CaNO3 is already given here, which is 0.10 m. So Ca2 plus, because CaNO3 is a completely dissolvable salt, so the Ca2 plus concentration becomes 0.10 m. So this is the initial concentration of Ca2 plus. Now let's write the reaction table. So you have CaOH taken twice becomes Ca2 plus 2OH minus. So initial, change and equilibrium. So we are starting with the initial concentration of CaOH with 0 concentration of 2OH minus. Now the change here is going to be plus S, so this becomes plus 2S. So the calcium concentration becomes 0.10 plus S, and OH minus concentration becomes plus 2S. Now, how would you calculate Ksp here? So the Ksp formula is Ca2 plus times OH minus square, which is 6.5 times 10 to the power negative 6, so which is 0.10 plus S times 2s square becomes 6.5 times 10 to the power negative 6. So 0.10 plus s times 4s square becomes 6.5 times 10 to the power negative 6. So which can become 0.10 times 4. So which becomes 0.4s square plus 4s cube equals 6.5 times 10 to the power negative 6. Now in this problem right here, because the actual value is nearly close to the original, so because the s value is really small, we can actually neglect the value of 0.10, so 0.40 times s square and focus just on the 4s cube. So this becomes complex. So let's try something simpler. So because we know that the s value is really small, the solubility is really small, so we can consider that 0.10 plus s becomes nearly equal to 0.10. So from this we can write that 0.10 times 2s whole square becomes 6.5 times 10 to the power negative 6. So 2s square becomes 6.5 times 10 to the power negative 6 over 0.10. So finally, when you calculate the actual value, so s value becomes square root of 6.5 times 10 to the power negative 6 over 0.10 times 4. So when you calculate the final answer, that gives you a value of 4 times 10 to the power negative 3. Yeah, so which is really small value, so which makes our assertion reasonable. Next, let's talk about the effect of pH on solubility. Now, changes in pH affect the solubility of many slightly soluble ionic compounds, and the addition of H3O plus will increase the solubility of a salt because that contains the anion of a weak acid. For example, when you have calcium carbonate, where you have Ca2 plus plus CO3 2 minus. So when you add H3O plus, the CO3 2 minus results in a stronger H3O3 bicarbonate acid, which increases the chances of having a much more stronger, much more soluble salt, which results in again the H3O3 minus again reacts with H3O plus, resulting in the aqueous carbonic acid, and then finally results in the release of carbon dioxide and water. Now the net ion effect of adding H3O plus to CaCO3 is the removal of carbon dioxide molecules, which causes an equilibrium shift to the right, so more CaCO3 will dissolve. So this is the idea behind how to affect the pH. So what are they asking next? Write balanced equation to explain whether addition of H3O plus from a strong acid affects the solubility of each ionic compound. First, you have lead-2 bromide. So the idea that the acid will affect it will only work when the anion of a when it contains the anion of a weak acid. So let's take lead-2 bromide. So lead-2 bromide, when you split it, becomes Pb2 plus plus 2 Br minus. So Br minus comes from HBr, which is a really strong acid. So the anion here is the strong acid anion, so which means that it does not affect the react with H3O plus, so therefore has no effect on its solubility. Next, copper 2 hydroxide. So copper 2 hydroxide becomes CuOH taken twice. So which when split becomes Cu2 plus plus 2OH minus. So OH minus is the anion of H2O plus, which is a weak acid. So which means that this gets affected by the H3O plus addition. So there is an increase in the solubility. Because remember here that H2O is a very weak acid. Next you have ferric sulfide, so which becomes Fe2 plus plus S2 minus. Now S2 minus is the anion of a weak acid, HS minus, a weak acid again, and is a strong base. So it will react with water to form HS minus and OH minus. Because both these ions are added to H3O plus, this results in an increase in the solubility. Remember that the pH is only changed when the anion of the salt is from a weak acid. So next, let's talk about how to predict the formation of a precipitate. Now, for a saturated solution of a slightly soluble ionic salt, generally QSP should be equal to KSP. Now, when two solutions containing the ions of slightly soluble salts are mixed, now if the QSP is equal to KSP, the solution is saturated and there will be no change. If the QSP is greater than KSP, a precipitate will form until the remaining solution is saturated. And if QSP is less than KSP, no precipitate will form because the solution is unsaturated. So next, let's talk about selective precipitation. So selective precipitation is generally used to separate a solution containing a mixture of ions. So when you have a precipitating ion that is added to the solution until QSP of the more soluble compound becomes equal to its KSP. Now the less soluble compound will precipitate in large quantity as possible, leaving behind the ion of a more soluble compound. So let's try to look at a problem. A solution consists of 0.20 m MgCl2 and 0.10 m CuCl2. So they're asking us to calculate the OH minus that would separate the metal ions from their hydroxides. So they have given us the KSP of MgOH2 and CuOH2. So let's take a look at. So notice that both compounds have 1:2 ratio of cation to anion. So we can compare their solubilities by comparing their KSP values. So because one is 10 to the power negative 10 and the other is 10 to the power negative 20, which means that there is a 10 to the power 10 times more solubility of CuOH2. So more solubility of MgOH2 in comparison to CuOH2. So which means here the one that is less will precipitate faster, and we'll generally write the dissolution equations. So first we have MgOH2 which splits and forms Mg2 plus 2OH minus. So the KSP value is already given as 6.3 times 10 to the power negative 10. CuOH2 can be written as Cu2 plus 2OH minus. The KSP value is already given. Now how do you find OH minus here? So it can be written as the square root of KSP over Mg2 plus, so which becomes 6.3 times 10 to the power negative 10 over 0.20, which becomes 5.6 times 10 to the power negative 5. Why do we use this? Because this is the one that is gonna result in more solubility. So this is the one that creates maximum amount of OH minus that will not precipitate Mg2 plus ion. Now how do you calculate the Cu2 plus ion? Again, use the same principle here, divided by KSP over OH minus. So the KSP value is already found here, and OH minus we have calculated from here, and calculate the Cu2 plus. Because the initial concentration is 0.10 m, virtually all of the copper ions is precipitated. So one of the best understanding of selective precipitation involves the formation of acid rain. Notice that the precipitation occurs when the nitric acid, the nitrous oxide, sulfur oxide, and other oxides generally undergo oxidation with oxygen, hydrogen peroxide, ozone, and monohydrogen oxide, result in the formation of the acid precipitation, which falls as sulfuric acid and nitric acid dissolved in rain and snow amount with their ammonia salts on the particles. So since the pH affects the solubility of many slightly soluble ionic compounds, acid rain has far-reaching effects on many aspects of our environment, where it can damage crops, it can damage walls. So lakes bound by the soil low in limestone become acidic. Lakes bounded by soil high in the limestone are buffered, and adding lime to the soil generally protects the crops. Though when you add more of these, so which means it creates acid fog, and you have sulfur and nitrous oxide emissions from coal-based power plants, and also nitrous oxide emission from car and truck, which can result in the formation of acid rain. So with that, we end the topic on ionic equilibria in aqueous systems. I'll see you all